So Thomas Zarbach is Division Director for MEMS Engineering, Manufacturing, and Test at Fraunhofer IPMS. And his talk today is on managing a high mix and low volume MEMS R&D fab by applying KPIs. Thomas, everything looks all set and ready to go. You have a total of 30 minutes. I'll still give you your full time, but we're running like 5 minutes behind schedule. So please stick to the schedule. So again, 25 minutes for the speaking portion, then we have a few minutes for Q&A. Otherwise, everything looks excellent. And Thomas, welcome again. Please go ahead.
Thanks, Mike, for the nice intro. And I'm going to try to stick to the minutes I have. So looking forward to talk to you today. Thanks for everybody for the attention, and thanks for having me, Mike and team. So as already pointed out, I want to talk about some manufacturing management perspectives today. Very brief introduction of the Fraunhofer Institute for Photonic Microsystems, IPMS. And we consider ourselves to be the worldwide leader, or we strive to be the worldwide leader in research and development services for electronic and photonic microsystems, targeting the application fields of industrial solutions, quality of life, and medical and health. Last year, we had 450 employees, and we have an annual turnover of 48 million, and out of that, 21 million coming from industrial acquisitions and contracts. So we are heavily working together with industry partners. Besides a 300 millimeter wafer fab for microelectronics, we do have a 200 millimeter wafer fab for microsystems, specifically for photonic MEMS. This is the focus I'm gonna take into my talk today. Our business model that we are supporting is basically going from TRL level 3 up to 8. So we usually have opportunities to support customers starting from research and feasibility studies, going through design and process development, demonstrator and prototypes, pilot fabrication, and also helping customers to transfer to a high volume manufacturing foundry fab, for instance. It's possible also for customers not to start from the left. They can also just get in somewhere in between if it's feasible. So we are very flexible on that approach here. And very brief overview on our key technology pools, I would say. So we do have surface micromachining that is enabling us to support micro-mirror arrays, CMOS. We have bulk micromachining that we use for microspeakers and scanning micromirrors. And we are very strong in MEMS on CMOS integration that is enabling us to do, for instance, thermopile arrays or also micro-mirror arrays. So here are some nice little pictures for some impressions. Also, I'm not going to stick too much to that level here, because yesterday you have heard the talk of my colleague Christoph Hohle regarding the MEMS-based SLMs, spatial light modulators for holography application. So I'm, as I said, going more to the manufacturing management perspective today. This is leading me to our clean room that we have. I think Christoph has shown pretty much the same slide yesterday already. So I want to also make this very brief. Everyone can read the details afterwards if he or she wants to. But the focus here is on, we are having a low volume and high mix clean room that we are running. Importantly to mention again might be that in lithography, we are now flexible between ILA and even up to DUV, which is nice for an R&D MEMS facility. We are qualified by ISO 9001. And also we do have an integrated MES system that helps us to go for KPIs and measure our line performance and to improve it to the benefits of our customers. Now, before I go into the deep dive, how we manage our, let's say, clean room, I would like to maybe give a brief overview on semiconductor fab setups and characteristics. So for that, I have chosen typical criteria or characteristics like the modus operandi of a fab, the number of products in a fab, the number of equipments in a process area, key personnel, variability, which means how much is your variance in your processes and your fluctuations inside the facility. This comes along with the number of products. And the speed resulting out of that, so we call it X factor. X means X times your theoretical cycle time if you never would have any waiting time in front of tools, if all tools would never be going down or having issues, and the number of wafer starts per year. So these are typical key measures that characterize several fab setups. Talking about these, of course, there are so-called high volume and low mix fabs. One example would be a typical one everyone knows, Intel. So high volume and low mix fabs are characterized. They are running basically all through a year. Usually they are not having so many products in their line, maybe below 10. On the other side, they have quite a lot of equipment per tool group. Let's say oxide etchers, maybe 20 and more for that type. They are having maybe 20 and more process engineers per area, like for instance, for dry etching. Their variability out of the smaller number of products is usually low, which is resulting in a very high speed, so short cycle times, which is typically 1.8 to 2.5 X factor. And of course, for every product they are running, they are doing several 10,000 wafer starts a year, which is a high loading, high volume perspective. On the other side, there might be, or there are high volume, high mix fabs, for instance, foundry fabs like global foundries. Of course, they're also running 24/365. They might have more products in the line, maybe somewhere between 20, 50, and maybe even more. On the tool side, maybe not as many as a high volume fab with low mix. Process engineers, maybe also somewhat smaller number of people per process area. The variability coming out of the higher product mix might be medium, at a medium level. And the cycle time in terms of the flow factor is maybe somewhere in the range of 2.0 to 3.0, so somewhat slower. And wafer starts wise, they are somewhere with several 1000s per product per year. And then on the extreme other side, we can consider our facility here, which we are consider a low volume, high mix R&D fab. So it starts that we are not running 365 days a year. We are running 5 days a week at 24 hours, giving us about 240 days a year. We have maybe, we do not consider it really products that we are doing. We do technologies and derivations out of those. So this is about 50 that we have here. The issue we are facing is we have only one, maybe in few cases, 2 tools per type. Process engineering wise, we are also limited to some maybe 1 to 3 process engineer per process area. And our variability coming out of the high technology mix is considered high. And that means on the other side that our speed is maybe significantly slower than in the other 2 facilities here, like flow factor 5 and above. And also, of course, we are not a high loaded facility. We are running maybe 250 wafers per year per product. So these are the characteristics to show you the, let's say, the tension between the setups. And now I would like to, of course, deep dive into the right column and still show you how we manage to be flexible, consider that cycle time is important and time to market as well, and trying to define the sweet spot between the boundary conditions we are facing and still offer a good service to our customers. And the typical approach here is that we call it our pyramid, which everybody knows. So you have to follow through with cycle time and time to market. You have to offer a good quality, which comes with a good stability. You have to be flexible. Specifically, we consider to be flexible out of our business model, ranging from tier 3 to 8, and there is cost perspective as well. And what I want to go through you, okay, and out of this, you have conflicting goals. So you cannot optimize everything in perfect directions. You will have interactions between the figures, and you have to find the best point that you can serve. And to do so, we set up different perspectives and measures and KPIs where we want to make sure that we can somehow handle that. For instance, for on-time delivery, I will show you how we manage cycle time spread and what that is, and how we do our material flow management. Process and technology, variability and stability are 2 things that are kind of also interfering. I think Christoph Hohle has shown yesterday into some insights with the MEMS-based SLMs for holography, what the efforts have to be. I just took 2 examples here, like for instance, deep silicon etching. We have 25 different processes with various differentiations in the depth of the edge step, with the width and the profile, that is resulting in several hundreds of recipes that you have to run at the equipments and handle them. Same for CVD. So for instance, for the USG deposition, we have variable thicknesses ranging from 50 nanometers up to 6,000. This is giving us, again, a few hundred process steps, recipes that we have to handle at the equipments. Equipment themselves, of course, are a big source of giving you stability, or maybe not. So this is something I want to show you a bit more in detail. Usually we consider uptime as a KPI to measure how the equipments are running stable, hopefully, and how we can also see what is happening when you have only one of a kind tool, and what it brings you if you maybe have second of a kind, a second type of equipment. And last but not least, when it comes to cycle time, I would like to show you in the end a model that is handling how is the interdependency between your cycle time, the X factor, the utilization of your manufacturing facility, and the variability, the variance. And this is called operating curve. So this is again the example from yesterday from my colleague, Mr. Hole, giving us the challenge with this spatial light modulators for the holography, having 500 process steps and considered long manufacturing time. How do we be able to still handle that? First is time to market. So this is something that everybody might know. If you have a certain number of wafers you are running, you have cycle times. For every lot or wafer, you get a cycle time, and you have an average cycle time for all the material, and then you have a distribution of your cycle time. And the distribution ideally is very tight around the average, and it's a normal distribution ideally. And when you have this stable situation, you can give your customer a so-called on-time delivery. So you are able to say, with a certain probability, I can assume and assure that a lot material is coming out at this point in time, and I can commit this to a customer. And then, of course, you have to hit this at least at 90%, maybe 90% on-time delivery or 95%. And now the issue is, how do you handle the so-called cycle time spread? How much is your cycle time deviating beyond the 5th percent quartile and the 95th? This part should be small out of your entire sample size. And this is something you should be able to control and to manage. How we do that? We have decided to go for so-called dispatch rule for our material flow management. So one example here, very general, is you have a process flow from one step to the last step, and you have a target cycle time for each step. And if you accumulate your target cycle time, you have a reference for all your lots and wafers running through the line. And at every point a material is being processed, you can see if it's either before the target cycle time or behind the cycle time or just on the target cycle time. And our dispatch rule says at a certain operation, let's assume this one here, with 2 lots in front, the lot with the higher delay against the target, its target will be handled first. And the idea is, if you do so, that in the end, you can manage to get your lots out as planned. Just to give you an example, here, this is a process flow with 150 process steps for a pressure sensor. You see the blue reference line, so the accumulated cycle time across all the steps. And by our dispatch rule, we have been able to get the real lot with the actual cycle time out in time. And this is as it should be. And the other point you can do with this approach is you can maybe also define different target cycle times for different products, maybe also for different projects, or maybe also for different customers. And if you are able to steer, you might then also be able to say, for a certain customer who is willing to pay some extra money for accelerating a process flow, we can then, and this is the same product behind, it's the same pressure sensor lot, it's a different one with the same flow, so to speak. We put it on hot lot priority, and with this, the lot has been able to run at almost 1/3 of the cycle time here, and it was still following very much the target that we have been put in the system. And so this is something we can use to be able to steer as we have planned and make sure on-time delivery is at a high level. So now this is another example I want to show you from, let's say, previous actual data. So you see here a lot that has been traveled across 150 process steps. You see again the target cycle time, planned target cycle time, and the actual cycle time. So what happened? The lot has been started later in time as planned. There was an issue behind, and we put it on acceleration mode, so hot lot status. And as you see, it was able to pretty much run very fast, being handled first at every tool. And as we have seen, it's covering up its target cycle time. We put it back on normal level. So here was the acceleration phase with hot lot. And then in the end, it was running at normal speed with the due date based rule. And it was pretty much still coming out as intended. So that's how it should be. This is how material should be coming out of the line. And this was running as intended. Our issue is here in this example, even it was better than at the left side, the lot has been started as planned. It was cycling through the line as intended. But then at one point, at one equipment, the equipment was going in an extended tool down. So we had a longer issue, maybe not 1 day, but it was like 1 month. No available parts to be repaired. And as I mentioned, when you have only one-of-a-kind tool situation in your clean room, this is really giving you a headache. And then if you have the tool back up and running, you might even accelerate a lot, but it's not maybe hitting your intended and planned cycle time or let's say target date. And this is of course an issue. And with that, we of course now are striving to go how to tackle that. We do not have the clean room space to put extra tools inside. We are also not having the money as a publicly funded institute. What we are doing now, we are looking into partnerships and potential corporations to maybe use other partners for backup equipment that we can use and qualify. And in case we have an extended tool offline, can use these resources. To measure that, to see if our tools are stable itself or themselves, we have set up a KPI called uptime stability. Usually everyone knows average uptime, and if you measure average uptime, things should be fine. The issue is you need to have stable average uptime. And what we did is we said, it's important over a period of time, let's assume 1 month with 20 working days in our case, at how many days in these 20 days we have an uptime that is above the planned and needed cycle time, uptime, sorry. And we can measure that, and then you can make a fraction out of those two. And let's say, for instance, you have 20 days, and out of these 20 days, 10 days, your uptime in the real world was above the one you are planning with, your uptime stability would be 50%. And the correlation is if you have a bad uptime stability. So here you see a histogram for many days that have been put in some analysis, uptimes from 1% per day up to 100%. You see that at many days, the uptimes have been deviating above 30%, maybe 50%. Of course, also some of them being in the 90s and above. But the correlation is your target cycle time has been violated in many days within the same period, right? And that is another example, a good one. If you look at this tool, it has been at a very high uptime, almost all of the days, above 80% and more. And here you can see for the same period, observed your cycle time has basically followed your target cycle time. That means stable uptime is key, and you can measure it by this uptime stability approach we have defined. The other issue is we had the chance 3 years ago to convert our line from 150 to 200 millimeter, and we took the opportunity to get new equipment, state-of-the-art 200 millimeter equipment. And we knew before that there's a so-called tube curve effect. And the tube curve effect says that when you get a new tool, and it might also refer to, let's say, new devices that you build up, usually in the beginning, you have early infant mortality failures that over time, when you analyze and get them fixed, go down, which means your reliability or uptime goes up. And over time, when it's many years go by, you have wear-out effects where the issues are coming back up. And the tube curve says in the beginning you have issues, then you have a stable period with high availability, high reliability, high uptime. And at the end of the lifetime, it's going up again. And what we have done is we have put measures into our equipment purchase process by putting specifications in place towards the equipment suppliers to really ask them to provide these uptimes and mean time between failures, and have just put this into the contract. And of course, afterwards had the chance to also ask the suppliers to stick to the agreed values. And just to give you an example here for some edge equipment. So these are several edge equipment chambers over time. So you see here from January 27 through October 2018. In the beginning, when the tools were being, let's say, hooked up and started and no material was coming along, it looked quite well. And then stressing the tools with the first material coming along, there have been issues coming up. And it took us many months to fix them together with the supplier. And let's say after 1.5 years, then we had a level of a stable uptime. Meanwhile, we can say it has been proven to do so. But again, the issues, as I showed before, if there's one extended tool offline, that can come along once in a while, of course. And if you have only one tool, it's still an issue. So this is again where we try to see on what can we do to get things transparent, to understand, to see how we can ask our suppliers to help us with the issue and be able to at least have a certain level of stability that turns into predictable cycle times. And last but not least, there's a model that I would like to introduce to you where we have the opportunity to understand what is the correlation between cycle time, your fab loading, and how does this behave. And we call this model operating curve. It is showing the dynamic performance of a production system. And the behavior of this correlation is like this. It says, if you have a low utilization, you have a low cycle time. And the higher you put your utilization of your clean room, there will be some point where your cycle time is behaving in a highly non-linear fashion. So the increase is very steep. The slope is getting very steep. And this model gives you the opportunity to see where is your operating point. So you can say today I'm running the fab at 80% utilization and I can understand what my cycle time is. And of course, now you can see, depending on what the market is asking, you can then see when I increase my utilization, what does it mean in cycle time increase? Or if I want to decrease my cycle time, what do I have to, let's say, take my utilization back? And this is how this operating point behaves along the curve. And the curve itself is calculated by this formula. I don't want to get into details here. The important point is the so-called alpha here. And alpha is called coefficient of variation, the variability as we call it. And this variability factor is, you can correlate it to certain, let's say, fab setups. For instance, if you have a high volume fab like Infineon or Intel, their alpha value will be low, which is good. And if your alpha is low, the curve is for a long time going very flat and just very much at the highest utilization level is increasingly going up. At a foundry fab, maybe like, for instance, X-Fab or also like Global Foundries, alpha is considered usually to be somewhere above 1. And then the curve behaves like that. It's going up earlier in the utilization. And when we consider my facility running at alpha definitely below, above 2, the curve might be going like this. And now let's say we have an operating point here, utilization at 50%, and we would like to increase it to maybe 66%. We then would have to accept a cycle time increase that is pretty high. And this is something where when you have the opportunity to understand that, you can then make good decisions, right? And now if you be able to decrease your variability by, let's say, increasing your uptime of the tools, having less extended tool offlines, maybe having platform approach, not too many process derivations, as we have seen, for instance, from Silterra, going for platform approaches. This would help to decrease your variability. So alpha is going down and the curve is flattening. And with this, you can then either earn the benefit in case you increase your loading. You can put some extra wafers in your facility and you will stick at the same cycle time level. This is from here to here. Or you can say, I go from here to here, which means I stick with the utilization I have and I earn acceleration in cycle time and time to market. Okay, so that's the model. There are some more facts and figures right here that you might be able to look into afterwards. I don't want to spend too much time here. This is what the impacts are and how it behaves. So this is something you can look afterwards because I would like to stick with my 30 minutes. 2 minutes from now. So if everybody is interested in this, I have some literature here. You can look into that. And my conclusion will be basically, what does it help our customers that we are able to control the line based on the models I have shown? One example is regarding time to market. There is an industrial partner that is running with our institute for many years in the CMAT development. And this customer has ordered a hot lot option to accelerate time to market. So this is something we can do. Another example is there's a customer going into thermopile array development and pilot fabrication, and he wants to be flexible in terms of having different generations at different TRL levels in our manufacturing facility. And for that, he is striving to keep up with his market leading position. So this is also something we can help with. And the third example is quality. So there's one partner which is using photodiodes that we materialize here, and he has asked for superior quality, and we have been able to deliver that compared to other second source suppliers. And so this is also something that we came up with. This is helping to have this customer now for many years. So concluding for that, it is essential that you know the status of your clean room when it comes to quality, which is something that is given. You have to be at high quality all the time, so you should not jeopardize there. You need to be flexible. You need to be able to deliver certain speed, cycle time, time to market. And of course, there's also the cost perspective. And just one example to give you, which has been shown by the CEO of one of our key partners last year in November at the Microfab Summit, Dr. Schieferdegger from Heimann Sensor. He has stated that the cooperation with IPMS, having the different capabilities, as you can see here, was giving this company an advantage of about 6 years time benefit from their other competitors. So we have been able to help them in this cooperation to develop something that is giving them a heads up of 6 years, which I think is quite impressive. So having said that, I'm looking forward to maybe 1 or 2 questions, and thanks for your attention.
All right, Thomas, thank you very much for the talk. Thank you for sharing the your contact information here. Yeah, and that's very impressive from Heimann Sensors that they accelerated by several years because they worked with you. So that's great. We can take a few questions and then we're going to go to lunch. I wanted to also show one more thing on Brella. But yeah, if there are any questions for Thomas, we can take those now. Thomas, maybe just I'll ask a question. Fraunhofer IPMS this year, what are some of the big things that you guys will be introducing? What's new for you this year? Anything that you can highlight?
Yeah, actually, I think one thing that has been highlighted yesterday by Christoph Hohle, we are now into the so-called 3D real holography topic, which is something pretty new. We think that is also maybe changing some things in the future. We are still together with Arioso, with the hearables. I think Holger has talked about that yesterday.
Yes.
And overall, of course, we are usually looking into other perspectives. Fraunhofer is currently looking into quantum and neuromorphic computing as an entire thing across Fraunhofer, where we also play a role as IPMS. So this is things that we are looking into this year and in the next years to come. Yeah,
that's great. Yeah, Fraunhofer IPMS, you guys certainly, there's a lot of innovation coming out of your organization and a lot of exciting things. So we're seeing a lot of press releases and other announcements that are coming out. So encourage everybody to reach out to Thomas via email or via Brella and his colleagues as well. Check out also the booth for Fraunhofer on Brella. And again, get in touch and discuss further, please. Thomas, thanks again for your talk. Really appreciate it.
Mike, thanks for having me. I appreciate it as well.